All right, friends and neighbors, welcome back. We are working through our review section before we take that CCNA exam. Now, this is volume 1, chapters 11 through 20. Do I know this already? Questions, but with a little bit of twist. So in chapter 15, there were lots of subnetting questions. So I kept all of the work that I did to answer all of those questions in there as well. So it's not just the questions, it's all of the, the sort of, I don't know, the math work that goes along with all of those questions. So that's in there. Also, chapter 20 doesn't actually have any do I know this already questions. So I just kept the whole thing in there because the author thinks, and I think, it's an important chapter to review. So it's all of your knowledge about routing and troubleshooting routes, and then also trace route and ping and all of those things. So I kept the whole thing in there. So there you go. On to the do I know this already questions. So host A is a PC connected to switch 1 and assigned to VLAN 1. So it's in a network, and that network belongs to a VLAN. Which of the following are typically assigned an IP address in the same subnet as host A? Choose 2. Well, your router is always going to be on your network or your subnet, and other hosts in switch 1, VLAN 1 would also have to be on the same network. Question number 2, why does the formula for the number of hosts per subnet, 2 to the h minus 2, require the subtraction of 2 hosts? Well, now we know what that is. The reason for that is that we have one address for the network or subnet itself and one address for the subnet or network broadcast. So 2 to the h minus 2. Question number 3, a class B network needs to be subnetted such that it supports 100 subnets and 100 hosts per subnet. Which of the following is workable for the number of network, subnet, and host bits? Choose 2. Well, we know that if this is class B, we have 16 bits that we can fool around with, right? 16 bits in the host portion. And we know that if we had to create 100 subnets and we needed 100 hosts, each one of those would require a minimum of 7. We also know that it's a class B, so there's 16 bits in the prefix that we can't touch. So the first number is going to be 16. We can't touch that. The second number, well, we can get away with anything 7 or above, as long as the two numbers add up to 16. So that would be subnet 8 and host 8, or subnet 9 and host 7. Question number 4, which of the following are private addresses? Choose 2. Well, we just saw the graphic, right? It's 172.31 was the answer, and 192.168. Both of those fall in those ranges. Question number 5, which of the following are public IP addresses? Choose 3. Well, anything outside of the private addresses from RFC 1918. So the answers here are the 9, the 192.1, right? It's not 168. Careful on that one. And then the 1net. None of these are private. They're all public. Question number 6, before Class B network 172.16 is subnetted, what parts of the structure of the IP addresses in this network already exist and with a specific size? So this is referring to the structure of the network itself. The answers there were A and C. This is a little bit of a tricky question. So the network and host portions are already there, and we're going to manipulate this by putting a subnet field in there and determining what the addresses are. Question number 7, consider the size of the network, subnet, and host parts of the Class B network 172.16.00 without any subnetting. Compare that to an updated plan that uses one mask for all subnets. Which answer best describes the size changes? Well, remember that we are going to be stealing, the minute we subnet, we're going to be stealing bits from the host portion, and that means the host part has to get smaller. Okay, did you know this already? Well, now we're really well equipped to answer these, but here we go. Which of the following are not valid Class A network IDs? Choose 2. Both B and C, 130 is not valid because that's in the Class B range, and 127 is loopback, so that's not valid either. Which of the following are not valid Class B network addresses? Well, E, all of the ones in the book, they're actually valid, so there's nothing wrong with any of them. Which of the following is true about the address 172.16.99.45's IP address? Choose 2. Well, the answers were B and D. This is a Class B network, and there are 16 host bits. We know that because it's Class B, and so the 9945, that's a representation of the space that is allocated to the host portion. Which of the following are true about IP address 192.168.6.7's IP network? Choose 2. Well, this is a Class C, and so we know the network address is 192.168.6.0. We also know that the default mask for Class Cs is 255.255.255.0. Which of the following is a network broadcast address? Well, the only answer that fit was 172.30.255.255. Remember that the entire host portion has to be converted to once, so that's why it's 255.255. So which of the following answers lists the prefix CIDR format equivalent for 255.255.254.0? Well, now we know how that all comes about. If it was 255.255.255.0, that would be /24, so this is /23. Which of the following answers lists the prefix CIDR format for equivalent of 255.255.255.240? Well, that's more than 24, and it turns out it's 4 more, so this would be /28. Which of the following answers lists the dotted decimal notation for /30? Well, you know it's at least 255, 255, 255. We need 6 more, and that means .252. Number 4, so if a PC's IP address is 1055.66.77 with a mask of 255.255.255, which is true about the host, subnet, and network bits? The trap here is that you start off with a Class A, and then you get a mask of Class C. I'm confused. Which one do we use? These look like Class full, but that's the trap. We're not talking Class full anymore, right? So the network is still going to be 8 bits. The subnet now is going to be 16 because we stole those middle 2 octets out of the host portion, which was originally 24 bits. So the host bits are 8, and so that is the only answer that sort of fits here. Question number 5. A PC's IP address is 192.168.9.1/27. So the tricky part here is that they're not giving us the mask. We have CIDR notation, which is true about the host, subnet, and network bits. Okay, well, at first glance we go, oh, that's a Class C. And it is a Class C, but it's a subnetted. So what do we now know about the arrangement of that last octet? Well, the network bits are still 24. The subnet bits are going to be 3, and the host bits are 5, because that /27 means that we stole 3 bits into the host portion. Which of the following is true about classless IP addressing concepts? And the answer there was D. We are ignoring the class rules right now. It's our starting point. We look at something and we go, okay, because we started off with this class, we know that you're subnetting or supernetting, right? And so we know how you manipulated the mask, but we are pretty much ignoring all of those base rules at this point. Question number 7, which of the following masks, when used as the only mask within a Class B network, would supply enough subnet bits to support 100 subnets? So the key here is that we need 100 subnets. How do we get 100 subnets? Well, you can say I'm going to create a subnet field of a certain size, or I'm going to have a certain number of host bits available. And there were 2 answers that did that. One was a /24, and what that means is that if you're subnetting a Class B and you steal 8 bits, you created 256 possible subnets because you stole that whole 3rd octet for subnetting. And in the last answer, you stole even more, right? You stole 14. So you created a whole bunch of subnets. They're all really, really small subnets, but that was the answer there. So those 2. So here are the did you know this already questions. If you examined all of the addresses in one subnet in binary, which of the following would it be correct about the parts that would be equal? Remember that if all of the nodes are in a particular subnet The only thing that would change for each node would be their host address in binary. In a subnet, that subnet field would be the same for everybody, and so would the network. So the answer was D. Number 2, which of the following is true regarding the binary subnet ID, subnet broadcast, and the host IP address values? Choose 2. Well, now we know the answer to this question, right? If we're talking about the subnet ID, we know that the host portion is going to be all zeros. And if we're talking about host IP addresses, they must not be zeros. So that was the answer there was B and D. Now, if we want to push this a little bit farther, we would know that the broadcast address would be all ones in the host portion. Number 3, which of the following is the resident subnet ID for the IP address 10.7.99.133? Well, for this one, you would just know that the mask would actually be 255.255.255.0. And if you did the ANDing, it would zero out the last octet. So this one is actually pretty straightforward, 10.7.99.0. But which of the following is the resident subnet ID for the IP address 192.168.44.97/30? Now the trick here is that /30. What does /30 look like? Right, that is 6 bits in the last octet, right? So these are very, very, very small subnets. So if you converted 97 to binary and then you put a mask underneath there that was 6 bits with 2 zeros, the 1, that last digit, would be zeroed out, giving us 96. Number 5, which of the following is the subnet broadcast address for the subnet in which the IP address 172.31.77.201 resides? Now, the tricky part there is that's a /27, right? So you figure out what the host bit's size is, how many bits are left in the host portion. Well, we know that if the host portion is only 5 bits and we put all ones there, then that would give us 223 on the outside. And maybe this one's actually worth doing on our spreadsheet. So if we take 172.31.77.201 and we take a look at what the mask is, right? So that mask would actually be, right? So that would be our mask. Now we take a look at where all the action is happening. It's happening in that last octet. Well, what does that last octet look like? Well, 201 converted to binary, 128, 192, we need 9 more. Okay, so not 32, not 16, there's 8. There we go. And then if we take a look at the binary for the mask, it would be this. And maybe we'll do the ANDing right here. So if I do this ANDing process, then I would get a network that looks like this. I would get 1 1 0 0 0 0 0 0. Well, what is this address? This is the 192 network. Well, what if so we can see all zeros in the host portion here, right? So there's our host portion. And so that means that my subnet here is 172.30.177.192. Well, what would the broadcast be? We need to take this exact same ending and put all ones in the host portion. So that would look something like this. Well, what is this value? Turns out it's 172.31.77 dot, well, what's 192 plus 31? Turns out it's 223. So that's how you would work through that problem. That was a tough one, so I thought we'd do it here. So this last one is a little bit of a design problem. You are building a DHCP server, and we need a DHCP scope that contains that provides the last 100 usable IP addresses in the network. Now, the first time I looked at this, I was like, oh, this is pretty easy. But we want is the last possible addresses in the subnet and specifically the last 100. So if we figure out what the range might be, then we're in much better shape and we can see which one of the answers would appear in the last 100. So it turns out that if you're a /23, then the network is actually 4.0. 10.1.4.0 is the network, right? And then in that subnet, you have a big address space. So the address space for this subnet is actually 4.0 to 5.255. And so an address that would appear in the last 100 would be 5.200. So did you know this already? So we have a Class B network, 172.23.0.0. We need 100 subnets with the largest needing 500 hosts. Okay, so we got a Class B, we need 100 subnets, and we got 500 hosts in the largest one. We also need to accommodate for 50% growth. That's a lot of growth with a single mask. That means that all the subnets will use the same CIDR notation, whatever it is, /27, /19, whatever it is, they're all going to be the same. How many masks, in other words, how many different subnet masks could you apply to all the subnets to meet this requirement? The answer is there aren't any. So let's see why that is. So I worked this out. Here's our problem, 172.23.0.0. We want 100 subnets and the largest subnet 500 hosts with 50% growth. Now, for at least 100 subnets in a Class B, right, we could use a couple of masks that'll get away with it. Remember that if we want to create 100 subnets, right, we're going to steal bits into the host portion. So how many bits do we need to steal? Well, if we steal 1, that's 2 subnets. If we steal 3, that's 8 subnets. 4 is 16. 5 is 32. 6 is 64. We need to steal 7 bits so that we can create 128. Remember, we're doing this on powers of 2. So we need at least 7 bits. But 8 bits would also do it. 9 bits would do it. 10 bits. So there's a whole bunch of combinations that would give us 100 subnets. But the next requirement is that we need 500 hosts in the largest subnet, which means that we need a certain number of bits for this 500 host subnet. Well, how many bits do we need to have for 500 hosts? Well, 8 bits is 256, right? A full Class C size address space. And so 8 bits gives us 256, so we need 9 bits to give us 512 possible. So that means that if we're just starting with a Class B, then we go, okay, cool. I need 100 subnets, so I need at least 7 bits. All right, and then for 500 hosts, I need at least 9. 7 plus 9, I'm at 16. That sounds pretty good, except, well, we got to account for that growth. So the 50% growth means that we actually need 750 possible in that largest subnet. And if we were growing our subnet numbers, we'd need 150 subnets. And so, you know, if we start off with, okay, we had 9 bits, now we need 10 bits for hosts, well, we don't have enough for the subnets. And so the answer here is that there's no answer to this particular problem. Question number 2, subnetting design. Okay, 200 subnets. We know what we're going to do then. 120 hosts per subnet, a little more reasonable. 20% growth, also a little more reasonable. Which of the following answers will work? And so there were 4, you had to pick one. And the answer was choice B, the 10 net with a /22 CIDR notation or a /22 subnetting. So let's take a look at that one. All right, so the thing that's going to get us is the growth thing. So 200 subnets and 120 hosts per subnet with 20% growth means that in the end, you'll need about 240 subnets and 154 hosts per subnet. So 240 subnets, well, let's see how we figure that out. Well, if we did 7 bits, like in the last problem, that would be 128. So we need 8 bits so that we can create all of our subnets. Now for 154 hosts, well, let's see. If we started off with 120 and did 7 bits, that would be fine. But of course, our growth gives us 8 bits for hosts. And so if we take a look at all of these answers, right, this /25, well, the /25, that's actually only 7 bits for hosts, so that's not going to work. This other one down here, /23, That looks like it's got enough room for the hosts, but does it have enough room for the subnets? And it turns out it doesn't because it's a class B. And a /23 would be 7 bits for subnets. And this bottom one here doesn't make any sense. That's just a class full address space, and that's not even doing subnetting. So the only one that answer that works is the 10net with a /22. Why? Because we are creating a lot of subnets, right? That is 14 bits taken for the address space for all of the subnets, and you've got 10 bits for the host. So plenty of room for all of those subnets. So question number 3, the class B network of 172.19. So again, a class B with a single subnet mask. So everybody's going to use the same mask again. Choose the mask that provides the highest number of hosts per subnet while supporting 1,000 subnets. 1,000 subnets. This is a big number, but we can do this. So it turns out the /26 will do it for us, but let's see why that is. Now in this particular problem, and for most, I think, I like to occasionally break things out into binary so we see what we're dealing with. Now when I need 1,000 subnets, right? If I take 8 bits for the subnets, that's not going to do it. That's 256. 9 bits gives me 512 subnets, so I need 10 bits so I can get 1024. So this is the mask that I will have. That mask right there, at a minimum, is going to be, well, 26. So we got 8, 16, 24, and then 26. Now, one of the other things you can do is they're being a little tricky here, and they're saying, well, what is, we've got all these different mask types in the notation. So maybe what we could do is we could say, well, what is this one? This one's actually /24, right? And what is this one? Well, 255, 255, 255, 192. And this one down here is going to be 8 plus 8 plus 6. So that'll be /22. And /28, well, that's 8 plus 8 plus 8 plus 4. So this would be 255, 255, 255. And what's 4? 128, 192, 224, 240. And sometimes it's nice to do that just so that you can say, well, I understand the nomenclature, and I'm not trying to figure out what, all the different formats for each particular answer. But the real meat and potatoes here is understanding how many bits we need for the subnets. So when we take 10 bits for the subnets, we have 6 left over, and that would give us 64 possible hosts per subnet. Okay, question number 4, another class B network with a /22 mask. Okay, so we know what that looks like. When listing the subnets in order, which of the following would be true? So the thing to do here is to say, all right, if I was going to write them all out, what would be the patterns? And so that's what this question is asking about. Now, it turns out that the answers were C and D, the 64 possible subnets, and the last subnet was 172.32.52. But let's see how that works out. And it's helpful to write it all down and see what we're dealing with, right? It's just like a word problem that you used to do in math. So if we break this out into binary, and we're given the /22, well, that's just 8 plus 8 plus 6 more. So this is what the mask looks like. So that right there is the bits stolen. And we just ask ourselves, how many subnets did we just create? Well, 6 bits in a class B. Well, 6 bits stolen, no matter what network you're in, you're going to create 64 subnets. But now we also know, because it's a class B, the size of each subnet, which would be 10 bits of addressing for the host. So we create 64 subnets. We know that that's one of the answers. But what would the subnets be? Well, we could write them all down, but there are 64 of them. So maybe there's a faster way or a pattern that we can notice. So if we write down the first subnet, right, and we begin with the class full address space, and then we say, well, if I put the highest possible number, well, I suppose you do it up here. If I put the highest possible number right there with all zeros right there, then it would be 3.255. That would be my range. Another way to do that would be to convert 1023 to binary and put that in there. But Whatever way makes sense to you, right? We've done a couple of ways. That would be our first subnet. Well, what's the next subnet? 172.34.0. Okay, so that pattern would be 0.000000100. Now we fill in all ones to get the highest. Well, it turns out that that would be 172.37.255. Now, if I'm looking right here, I say, okay, well, I added 4. Let's see if it works out again. Well, 172.38.0 is the next subnet, goes to 172.30.11.255. I go, oh, okay, all right. Well, that looks like a pattern. So I could just do all of the numbers that are multiples of 4. So you could do that. Now, it also works out that in this particular case, right, in that octet, 256 possible values divided by 64 is 4. But we can also work backwards. We can say, all right, if this is the highest value that was there, and we know what was going on here, right? If I said, well, this value was 1 less, and then I just subtracted 3 from that, then I would get 252 as the highest, and then I could get, the next one down just to do some checks. So there's some patterns that you can look at, some shortcuts, but you sort of have to know what you're looking at. But those were the two answers, right? So this was the highest subnet, and we created 64 possible subnets because we stole 6 bits. Question number 5, which of the following are valid subnet IDs for a private network 192.168.9.0 using a /29 if this is used throughout, meaning the mask, the /29? Well, the answer was 9.144. So let's figure out why that is. Then again, we rewrite the question. And now this is a class C. So we're only dealing with 1 octet's worth of space. And we know that this is a /29. So we start off with a /24. So that's 5 bits of addressing for subnets. So we created 32 subnets. And we could write them all down again. Or again, we could try to look for patterns. Now we know that if I stole 5 bits for subnets, then I've got 3 bits left over for hosts. So I've got 8 possible addresses in the hosts. And in the first one, for example, it would be 0 to 7. If we wrote down what that first subnet might be, and then we just sort of did a little calculation here, then we would say, okay, the first one is 192.168.9.0, and we know that there's 8 possible. We start counting at 0, so it's 9.7. The next subnet up would just be one more than this one, so 192.168.9.8. We'll add 7 to that, and we go 192.168.9.15. We'll do one more to have the pattern emerge, and we get 192.168.9.16. Okay, so we have clear multiples of 8. And so the shortcut here is, are any of those answers divisible by 8, or do any of them, are any of them just crazy outside of what was there? And so the only one that fits is 192.168.9.144 because 8 goes into 144 evenly. Question number 6, which of the following is not a valid subnet ID for private network 172.19.0.0 using a /24 if this is used throughout? So again, everybody's using the same mask. A lot of these problems are same mask problems. Well, the only one that doesn't make any sense whatsoever is 172.19.0.16. And the reason it doesn't is because while there's a 0 here and you go, well, wait a minute, if we start with a class full address space, wouldn't I start there? And the answer is yes, but it would be all zeros everywhere. And so that .16 doesn't make any sense. But again, we'll take a look. Now, the cool thing about this problem is that it's a /24. So that means the entire third octet is where all the action is. This is where all of the subnetting happens. So there should be nothing going on in the last octet. There will only be 2 values there. The lowest will always be 0, right? No matter what the subnet is, that it'll say .0 for the subnet address. And no matter what's happening, it'll be .255 in the last octet for the broadcast. We just have to figure out the third octet. Well, If it's in the third octet and we're just counting through that, then we start at the class full address space and then we just go the 1 net, the 2 net, the 3 net, and so on. So the first subnet is 172.19.00, and the range of addresses goes up to 0.255. We add 1, and we get the next subnet, 172.19.1.0, all the way up to 172.19.1.255. It's really, really straightforward. And so it will go through all 256 possibilities to get the subnets, and they would all just be numbered according to what was going on in the third octet. So all you had to do was figure out which ones don't fit that model. And the one that didn't was that silly .16 in the last octet. All right, we'll close out or get ready to close out with some subnetting fun facts and some foreshadowing. Obviously, with these problems, these were a bit challenging, I thought anyway. And so you got to remember your binary and your powers of 2. They will save you more times than I can say. In addition, most of the examples so far focus on a single mask used throughout. So all of the subnets are the same size, they all use the same mask or the same CIDR notation, and that is where we always start with subnetting. Now this indicates that sometimes we use different masks within the same organization or within the same set of networks. So it is very possible to take a whole bunch of subnets and make them equal size, and then take one of those subnets and make it, well, glued with another one to increase a chunk of the address space. Or you can take a subnet and further chop it up into smaller and smaller subnets. When we do this, that's called variable length subnet masks, or VLSM. Another fun fact, normally we think of the smallest subnet that's possible as having at least a couple of addresses for nodes. So for example, a very small subnet would be 192.168.1.255 to 250, or 1.252, and the range would be 255. So the mask would be 255, 255, 255, 252. That only gives us 4 addresses, right? Because there's only, when you do .52 or when you do .252 in the last octet, there's only 2 bits left for hosts. So you say the subnet ID, the broadcast ID, and then 2 addresses for host, and one of them is going to be a router. But there's a whole RFC dedicated to allowing /31, only 2 addresses for a particular subnet. So RFC 3021 using 31-bit prefixes on an IPv4 point-to-point links, because there are no hosts. So that's where you can get away with it. If we can subnet, we can also supernet, which means we glue subnets or networks together. So if we started with a class C and we needed more address space, or we wanted to simplify routing tables, we might glue a class C network address space with another class C address space. That doubles the address space size, but it also reduces the number of addresses in a routing table. We'll do that later, but just a little foreshadowing. There's a whole bunch of stuff that we do with masks when we get a little more advanced and we get really good at this stuff. All right, time now for Do You Know This Already? Which OSs run on Cisco Enterprise routers and use a CLI that works much like the CLI on Cisco LAN switches? Choose 2. Well, the 2 answers there were pretty straightforward. They're the 2 that we've talked about, iOS and iOS XE. Which action would be true of a router CLI interaction, but not true on a switch that performs only layer 2 functions? Well, as we were just talking, switches don't get IP addresses on interfaces very often. So B. Question number 3, which answers list a task that would help make router interface G0/0 ready to route packets? Choose 2. Well, there's 2 things that we have to do. We need to give it an IP address and a mask, and no shut the interface. Now the tricky one on this thing is that one of the answers said give it the IP address and IP mask commands. So that's a little bit tricky. I'll actually show you that here in a second, how to do an IP address and a mask on an interface. And so it's not a separate command, it's all part of one. Question number 4, show IP interface brief on R1 lists interfaces codes of down and down for G0/0. The interface is directly connected to a LAN switch. Which of the following could be true? Now, this is actually a problem. I have a problem with this particular question in the book because you can get down for two answers. So whether the router or switch interface is shut down, you'll get down, and I'll show you that here in a second too. But the answer that the book was looking for was B, the switch interface is shut down. Which of the following commands lists the IP address but not the subnet mask of the interface? And the answer there is show IP interface brief. Question number 6, which of the following is different on the Cisco switch CLI for a layer 2 switch as compared to the Cisco router CLI? And the answer there was B, the number of IP addresses configured. Fewer IP addresses on a switch. All right, so let's go over those things on the router. So we'll focus on these two 2811s right here. And what I'm going to do is we'll give the two these IP addresses. We'll say, we'll make this 10.0.0.1, and we'll make this one 10.0.0.2. So I'm consoled in to the router on the right. We'll go to int g0/3/0, and we will say IP address 10.0.0.2. Now, if I do a question mark here, it wants the mask, but I don't need the keyword mask. I just say 255.0.0.0 like that. And then I would do a no shut, and that would bring it up. I think I already did a no shut on these. Okay, so that would be that interface right there. Now let's connect to our other router, and same thing. Config t int g0/3/0, and I'm going to say IP address 10.0.0.1 255.0.0.0. Okay, and again, just to be complete, I would do a no shut. I don't have to do it here. Now, let's take a look at our show IP interfaces brief. We can see a couple things. One is that it's up and up. So line protocol is up, right? So I have a link, and then I've got the protocol up as well. So the physical link is okay. The first one, you can think of this as what's the first check? Layer 1. What's the second check? Layer 2. Notice here that there is no mask shown here in this particular interface. Now here's the other question that I wanted to show you. Oops. Let's take a look at our integrated services router. And if I do a show IP interfaces brief, I can see that I've got for these interfaces here, I've got down and down. Now this module, right, this device has these interfaces here, but I'm not connected via all of those. You can see that the interface is down. And in this case, the switch is clearly powered up, right? I'm talking to it. So the interfaces, let's do, and here we'll do, maybe we'll just do a status. None of my ports are connected, right? It thinks they're not connected because my router interfaces are down. So this is my justification for the gripe about this. The only thing that's shut down here is the router interface. If I was just simply bring this one up, right, gig 0/001, right here, just bring this up. So that's this one here. So the only change that I made was with the router being shut down, the router interface being shut down. So that's my reason for the gripe with a particular question, but it's a little detail. There we go. All right, did you know this already? Router 1 lists the route in its routing table. Which of the following answers lists the fact from the route that the router uses when matching the packet's destination address? So we have to realize that the packet comes in, and the packet is going to have an IP address. And the router says, all right, which is the entry that I want to use with this? And the answer is going to be A and C, the mask, and then the subnet ID. And so when I AND the router table entry with the mask and the destination with the mask, they should be the same. PC1 sends an IP packet to PC2. To do so, PC1 sends the packet to router 1, which sends it to router 2, which sends it to router 3, which routes it to the final destination. All links use Ethernet. How many routers de-encapsulate the packet from an Ethernet frame during its journey from PC1 to PC2? And the answer was 3, D. They all do it. So remember that every time you cross a router, you're going to be destroying that Ethernet frame. Question number 3, after configuring a working router interface with its IP address and mask of 10.1.100/26, which of the following routes would you expect to see in the output of the show IP route command? Remember that you're going to have one for the network and you're going to have one for the router's IP address. So it makes sense that you're going to have a 10.1.100/32. But it also is going to be the network. Well, what's the network with this particular mask? Well, it turns out it's a .64/26, not .100/26. So A and D. Which of the following pieces of information could be listed in a correct IP route command on a local router? Well, you know you're going to have the next hop router, right? You can have that. And then we saw that we could use that interface command or interface argument as well. Question number 5, which of the following commands correctly configures a static route? Well, there was only one that made sense of those, and that was the standard static route, the preferred static route methodology. Right? Stay away from those proxy ARPs if you can help it. Question number 6, a network engineer configures the IP route 10.1.1.0.255.255.255.0 going out over a serial link command on a router and then issues the show IP route command from the enable mode. No routes for the subnet appear in the output. What could be wrong? Well, if your link is not up, you're not going to see the that route. So B, that the serial link was down. All right, the do you know this already or do I know this already questions. Question number 1, router 1 has a fast Ethernet interface 0/0 with an IP address of 10.1.1.1. The interface is connected to a switch. Okay, I get that so far. This connection is then migrated to use trunking. Okay, which of the following commands could be part of a valid configuration for router 1's F0/0 interface, assuming the trunk uses VLAN 4 as one of the supported VLANs? All right, so this is all about router on a stick, right? And so the two things that we need to do is we need to have a subinterface and we would use the encapsulation command. Router number 1 has a router on the stick configuration, okay, with two subinterfaces. G01.1 and G01.2. The physical interface is currently in the down state. That is no bueno right there. That is not going to be helpful for us. The network engineer then configures a shutdown command when the interface configuration for the subinterface 1.1 and a no shutdown command when the interface configuration mode is for G01.2 subinterface. Which answers are correct about the interface state for the subinterfaces? Well, it's pretty straightforward. Wherever you issued the shutdown, that's going to be administratively down. And G0/1.1 is going to be down because the physical interface is down. Question number 3, a layer 3 switch has been configured to route IP packets between VLANs 1, 2, and 3 using switch virtual interfaces. So this is the multi-layer switch configuration. And then we've got some subnets here, the 1, the 2, and the 3 net respectively, /25, that's the key. That was one of the answers in there to trick you into using the wrong subnet. The engineer issues a show IP route connected to show IP route connected command on the layer 3 switch consisting of connected routes. All right, so there's going to be 3 of them. Which of the following answers lists a piece of information that could be in at least one of the routes? The route will be connected to an interface that was VLAN 2. That was the only one that matched. And that should make sense to you. All 3 of these would be directly connected routes to a particular VLAN. So if you were going to write down what the routing table looked like on paper, you would see that appear somewhere. Question number 4, an engineer has successfully configured a layer 3 switch with switch virtual interfaces for VLANs 2 and 3 with auto state enabled by default. Hosts in the subnets using VLANs 2 and 3 can ping each other with the layer switch routing the packets. All right, pretty straightforward so far. The next week, the network engineer receives a call that those same users can no longer ping each other. The problem is with the layer 3 switching function If the problem is with the layer 3 switching function, which of the following could have caused the problem? Well, if somebody deleted the VLAN, that would cause a problem, or if somebody shut down the VLAN. The other ones didn't match because they weren't applied to these particular VLANs. Question number 5, a LAN design uses a layer 3 ether channel, okay, between two switches, switch 1 and switch 2, with port channel interface 1 used on both switches. Switch 1 uses ports G0/1, 2, 3, and 4 in the channel. Which of the following is true about switch 1's configuration to enable the channel to route IPv4 packets correctly? Well, we know that the IP address has to be on the port channel. And then it says this, I have an asterisk next to this one, the port channel is no switch port. Actually, as we saw from the configuration, you would use no switch port, but it would actually be on all the gig interfaces, right? Because we would tell them that we want them to be routed. So that may have been an oops in the book, or I may be reading the question wrong. But the key is that we're going to be no switch port because we want them to be routed ports, and the IP address will be on the port channel. Question number 6, a LAN design uses a layer 3 ether channel between two switches. Okay, same idea, switch 1 and switch 2. An engineer adds switch 1 gig port to the channel successfully, but later fails when trying to do the same thing with 0/2. Which answers list a configuration setting on port G0/2 that will cause the issue? Choose 2. Well, one of these goes all the way back to an earlier chapter. You can't put up an ether channel when there's a different configuration between the two sides. So they have to be the same duplex and same speed. And remember that you're going to do the switch port or the no switch port. So if you did no switch port on one and you didn't do that on the other, that would cause the error as well. Question number 7. A router has some routed and some switched physical ports. Okay, which interface subcommands would you expect to be supported only on the switch ports? Well, switch port access for the VLAN. That's the one that we need. Everything else was either in both of them or specific to routed. All right, our Did You Know This Already quiz. Question number 1. A PC connects to a LAN and uses DHCP lease on an address for the first time. Of the usual 4 DHCP messages that flow between the PC and the server, which ones does the client send? Well, we know that right off the bat. It's the discover and then the request after the server comes up with an offer. Question number 2, which of the following kinds of information are part of a DHCP server configuration? Well, we just configured that, so we know that we're going to give out the network or the IP addresses to lease, and then also the addresses not to lease. These are the excluded addresses. Question number 3, which answers list a criterion for choosing which router interfaces need to be configured as a DHCP relay agent? Well, we have to make sure that the subnet off of the interface has DHCP clients, but there isn't a server there. So that was A and C. Question number 4, a router connects to an internet service provider using its gigabit interface. With the IP address DHCP command configured, what does the router do with the DHCP learn default gateway? Well, we just saw that it adds a default route. In the following excerpt from a command on a Macintosh computer, which of the following parts of the output represent information learned from a DHCP server? Well, if we think about what we just configured and we think about the basics, we know that we need the IP address and the mask will have come from the server. All of this other stuff is interface specific or automatically figured out. Question number 6, which of the following commands on a Windows OS would list both the host IP address and DNS server's IP addresses as learned with DHCP? We saw that was ipconfig/all. All right, friends and neighbors, welcome back. Now we are going to tackle troubleshooting for IPv4 routing. And so we're going to do a couple tools and we'll do a bunch of demos on how to help you figure out, what might be wrong with your topology. So here we go, troubleshooting IPv4 routing. So in this video, we have our key topics. Of course, I'll go over those really quickly. And then we have our exam section. This is all about network access. We're going to actually review some of our network management access. And then, of course, this is really about troubleshooting. And so IPv4 for connectivity. We're going to take a look at the static routing. I have a topology configured for you. And of course, remember from the previous videos, the different kinds of routes we have. So we'll take a quick look at some of those. And this chapter has no do I know this already question. So here's our key topics, right? We've got tables. Our forwarding rules are all about the tables that we have. So we have the host routing, host ARP, we have a switch SAT, we have a router ARP, we have a router routing table. So lots and lots of tables. Get to know those tables, get to know the operation, and you've got it down. We're going to do some pings. We'll do that from the routers and we'll do it from the host. We'll do a comparison and then see some advanced pings. And then we'll talk about some of the reasons why they fail and what might be the symptoms that you get as a result of some of those failures. And then I've got a host configured that has a default gateway and one that doesn't. And so we'll see what happens there. And we'll do some really basic DNS configuration or IP host configuration stuff on the router. We'll talk a little bit about that. And then, of course, we're going to do traceroute, problem isolation using ping. Ping has got to be one of the most popular troubleshooting tools that we have out there. We call it proof of life. But it is really a program that generates ICMP echo requests in the hopes of getting an ICMP echo reply. So it's also sometimes called the responder function. There is no TCP or UDP involved here. It's just an ICMP message encapsulated in IP, v4 or v6, and then in Ethernet or 802.11. Different OSs have different behaviors, and we'll take just a real quick look at that, but we just have to realize that when you're on Linux, that behaves different than on Windows, which behaves different than on a Cisco device. Now, there is a difference between pinging from the host and pinging from the router, because the router, a lot of times, in addition to its different perspective on the network, it might know some things that the host doesn't. Now, when we get a ping back, sometimes we just want an answer. Right? I pinged you and I got a reply. So that's good. But ping can also be used for a little bit of timing. And so this bottom here is an example of some of the additional information. We have packet loss here. How many did I send? How many did I receive? And therefore the loss. But also we get a feel for the round trip times. And so we get a max, a min, and an average. And these can sometimes help us when we're trying to troubleshoot some delay issues. Now, like all troubleshooting or problem solving, we have a strategy or a methodology that we can employ when we are doing our pings. So one of the things that we do is we say, oh, a trouble call comes in, I can't get to the internet. And so a simple question is sometimes, well, what can you get to? And this leads us down the pathway of saying, well, okay, what is available to me and what isn't available, and that helps us diagnose the problem. So for example, well, I can't get to the internet, but can I get to my default gateway? And that really isolates or helps isolate the problem. If you can get to the gateway, well, it might not be a host problem. If you can get to the gateway, but you can't do anything with names, then it might be a DNS problem. So there's lots of ways to help isolate. The other thing you can do is say, well, can you ping your neighbor? Can I ping anything else that I might get to or might need to get to? And so these are ways to help narrow down where the source of the problem might be. So we're going to try to go over a couple of scenarios here in the demo, right? What happens when a host is missing a gateway? What happens if links are down? What happens if your router doesn't know the answer to the destination? So we'll break a couple of configurations and see what we get as a result of that. And then what happens if the router along the way doesn't know the answer. But those sort of point in the outward bound direction. What happens if you try to ping something and the problem is not in the outbound path, but rather in the return? In other words, the routers don't know how to get back to you. These are different problems. Now, the book talks about several root causes for failure: an IP addressing problem, an IP mask problem. Now, I've got a note on here. Look at our topology. In this chapter, all of the examples are 172.16 networks, and that would indicate that you're going to do /16 somewhere, right? But because the important part of the addressing is in the third octet, These are all /24s, and that's important to realize. It's really easy to screw up the masks and therefore change what a node is going to do or is willing to try to do. If we have a DHCP problem, right, if a node tries to get somewhere, now users don't know about DHCP or DNS, but if they can't get an IP address and try to go somewhere, well, that's obviously not going to work. And so DHCP problems, VLANs or trunking problems, right? Did you prune something? Are you in the wrong VLAN? These all cause problems. And don't forget your layer ones. Users also don't realize that they need link lights, cables go bad, ports go bad, all of these things. So we can have layer one problems in addition to all the other things that might go wrong. So we just don't want to forget all the places where we might need to look. Now the book also talks about extended or advanced ping, additional commands and abilities like specifying the source IP address for the ICMP echo. Now, we'll do a demo of this and we'll see the impact of it. But basically it comes down to this. If a router is trying to respond, or if you ping from a router, it's going to pick the interface that's on that direction. But that leaves out some troubleshooting steps that you might take. So the extended ping gives us the ability to specify connectivity to any one of the router's addresses. So you can substitute a different source IP for the ping, and I'll show you what that means here in a minute. I added here that there are additional features are not just for Cisco, and the screenshot on the side of me here shows all of the possible options that you have from a Windows host or from a Linux host or a Mac host. There are piles and piles of options, but people don't use them. So for example, you can specify that you want to record the route. You can specify the hosts over which you want this traffic to travel. And so the IP header can actually expand to include a whole bunch of IP addresses that you want to use on the way out. And so it's sometimes fun just to experiment with the tools that you have. Let me show you a quick example. So here is the output of ping, right? If I do ping without any arguments, and I see all of these things that are available to me. So I might do, let's just take an easy one. If I do ping-n2, and then I go out, right? So this just says, well, I'm going to do 2. But I can also do a ping-l, for example, and I might change the size of the ICMP packet that I send. And what this does is it sends a much larger packet and allows me to experiment with things like fragmentation, which may or may not be allowed. And so these are important tools that you can use. If I change the IP address here, now I get a response. And we can see that I'm actually sending a much larger packet. And those are just 2 examples, but I can also see that I can use ping with IPv6 just to get you started. Okay, now the minute we start saying things like names, we're probably talking about DNS, but we might be talking about some other mapping, a local mapping of IP host name and IP address. And then we can ping based on names as well. So there's nothing at all that says that you can't ping to a namespace. Now the nice thing is that this tests a couple of things. This tests not only connectivity, but also tests DNS lookups. Remember that DNS is actually kind of like the phone book for the internet. So when we talk about IPv4 addresses or IPv6 addresses, we're talking about the address space. But of course, people don't use addresses like IPv4 addresses. They use names, www.cisco.com. These are all part of what we call the namespace, and DNS, or the domain name system, is the thing that maps names to IP addresses. And so there are a couple of commands that you can use on a router to specify that you want to go to a DNS and use those lookups. I don't have a DNS configured in Packet Tracer, but I'm going to use another command to show you sort of what it looks like. And then we did the IP domain name because we're going to do SSH. All right, let's do a couple of quick demos. First up, I just wanted to show you that you can ping an address. So if I wanted to ping YouTube, for example, I can ping a name. Now, what actually happens? Well, the first thing that happened in order for this to work is that I had to do a DNS query, get the IP address of YouTube, and then I actually pinged the IP address. So that's what we mean when we say we can ping a name. All right, here is our packet tracer topology, and we're going to do a couple things here. The first up is we're going to ping around when we don't have a default gateway. So here is 172.16.1.2. It has no default gateway. So when I ping around, there are things that will work and things that won't. So if I try to ping somebody on my network, 1.1 for example, that works. That's this host right over here. If I want to ping my default gateway, well, that works too because my default gateway is on my network. But what happens when I ping somebody that's off of my network? Well, the host says, I'll try, but I don't have a default gateway, and that host is not on my network, so what do I do? Now, this is related to another problem. So I don't have a default gateway. That's why this fails, right? I never attempt to go to my default gateway. Now, we can verify that. If we take a look at the simulation, right? And I do the exact same ping. Let's see what happens. We'll put this down a little bit. Notice that the packet never actually goes anywhere. And this is because the host says, well, I processed my host routing table and I have no idea how to get there. Let's try something different. Let's try a mask problem. So now I'm going to go to my fast Ethernet interface and I'm going to change the mask from /24 to a /16. Now this host believes that instead of being on the 172.16.1 network, it now believes that it is on the 172.16 network. And we're going to do the exact same thing. We're going to try to ping, and we'll see what happens. We're going to run our simulation again. Now what happens? Now this message actually goes out. Why is it going out? Well, the host believes that it's on a much larger network, that the destination, 172.16.4.1, is not on a different network, that it is in fact on the same network. And so it goes out, but of course, that host is not out there. So 172.16.1.2 believes that it can get to the destination. Well, let's take a look at a different host. Now this host does have a default gateway, and it has the correct mask. We'll do a couple of examples here. All right, so I have passwords set up, so we're gonna go over those later on. If I take a look at my routing table, I can see that right now I know how to get to the 2net. I'm going to take away this network. IP route 172.16.2.0. And the reason that I'm going to take this away is because I do not want this router to know where it is, because I want to see what result we get when we ping. So now if we do a show IP route, we only know about the directly connected networks. Okay, so now I'm going to ping 172.16.2.1. Now that is this node on the other side of the topology. Now this is really important. This comes back from 172.16.1.254. And what that address is telling us is that I don't know how to get to the 2 network. Well, what does that look like in traffic? So it goes out from the host to my default gateway. Please help me with this. And we see that the router sends back an ICMP destination unreachable. So what we've got here is that you tried to go to this destination and I did not know how to get there. So this is an ICMP destination unreachable, type 3 destination unreachable. So that is the result of a router not knowing how to get there. So my default gateway doesn't know how to get to the destination. Well, let's fix that. And let's create a different problem. I'm going to go over here on this router. And if we take a look at this routing table, now there are only 3 networks here. Now this router knows how to get to all of the networks here, but I'm going to take away the 1 network. And so the difference here is that my traffic will know how to get out, but it will not know how to get back. Okay, that's an important distinction because our results differ. Here it's clear that a router, if it doesn't know the answer, is going to tell me that it doesn't know the answer. But now if I ping, what happens? Well, now this is real time, so the traffic is attempting to get out there. And it times out. So let's take a look in the simulation and see what happens. So the traffic goes out now, but we've told R1 how to get there. So R1 forwards it, and it gets all the way to the destination, right? Gets all the way there. And 2.1 has a default gateway, so it sends it back to its default gateway, but the default gateway does not know how to get back to the 1net. And so it's the same thing, but the problem is if we are troubleshooting from this host, we cannot see the answer. We cannot see what happened. We just get no answer. So it's a little bit like a black hole. We just send it out there and we have no idea where this actually broke. And so these are 2 important differences that we get when we're taking a look at the output from ping. Okay. Well, we saw that Windows uses a default of 4 pings. Linux is continuous ping. Let's fix what we just broke first. So now we're back to a fully functional topology again. And let's try pinging from a router, because this is something that we can do. And we can say ping 172.16.1.1, right? Now we see, first of all, that Cisco uses 5 pings. And if we were to open those up and look at the content of the message, it would be a little bit different. But that's not actually what we want to see from ping at this point. We want to talk about that extended ping. So if I ping 172.16.1.2, so I'm going to ping this node down here. And I want to use the simulation here because we want to see the address that it actually uses. So I'm going to do this. So the ICMP goes out. Now one question then is, what is the source IP address used by the router? Well, the router uses 1.254 as its source. It uses the interface that's closest or in the right direction to the destination. But this really doesn't test very much, right? So what we're going to do is we're going to use extended ping now. And we are going to specify a different IP address. Now, what this allows us to do is understand a little bit more about what the topology knows or understands. If we were trying to diagnose something, we might want to use a different IP address to determine how the routing is set up or if the routing works. So if I just use ping without any arguments, it starts asking me questions about what I want to do. So I'm going to say we're going to do IPv4. The target IP address is still 172.16.1.2. The repeat count is 5. Okay, now I could change that. Datagram size 100. Okay. Timeout. Okay. Extended commands. Yes. Now this is where I get to specify the different address. Now I can do this from whatever interface the router has. So I'm going to use 172.16.4.1 as my source IP address. Type of service, DF bit, no. There we go. Okay, so if this goes out now, we can see that my source IP address is now 4.1. And what this does is allows us, if we were testing the connectivity between routers or testing interfaces or networks, right, this will enable us to test whether or not my routes are all set up. That is what we mean by advanced or extended ping. Okay, problem isolation with traceroute or traceRT in Windows. Another extraordinarily common troubleshooting tool, very widely supported and used. Like ping, it depends on other hosts to send you messages back. So you send out messages and you're hoping that devices along the way are willing to respond to you. Its use is a little bit different than ping in that you're trying to test router interfaces along the path to the destination. That also means that you can test multiple devices along the way with one command. The path that we're testing is also called the forward route from source to destination as opposed to the reverse route. This is also a collection of the next hops along the way. Now, I suppose it's important to understand how traceroute works. The key is in the time to live field in the IP header. Every IP packet has a time to live associated with it. And if that time to live is decremented down to 0, the router that does that says, I can't forward this anymore. And it sends back to the host an ICMP time exceeded message. That's how we remove continuously circulating packets or packets that are caught in a loop. Now, traceroute leverages this by sending messages out first with a time to live of 1, and then with a time to live of 2, and then a time to live of 3, and so on. So the first router gets it, the time to live is 1, it decrements it to 0 and sends a message back. And you go, aha, I know the first hop out. And then you send another traceroute message, actually an ICMP message, out with a TTL set to 2. So it gets by the first router, gets to the second router, and then the TTL is back down to 0, and that router responds, and so on and so on and so on. And of course, we have extended traceroute as well. So here is a host that has the traceRT command, and what I'm going to do is we're going to trace to the other side. Now, this is not from the router, right? But this shows you the hops along the way. So this is my default gateway. There is the next router in the line. That's this one here, and then finally the destination. But of course, what this is telling us is that you can also use traceroute, or the fully spelled out traceroute, 172.16.2.1 to the same destination, right? So Cisco devices and hosts both have traceroute, and it's really important to understand how that works. So let me do the, we'll do it from here. Do the same command again, and we'll do the simulation to show us how it actually works. All right, here we go, traceroute. All right, now when this, we'll let it go out to the multi-layer switch. There it goes. And if we take a look here, again, what we're looking at in the IP header is for that time to live right there. So the time to live is set to 1. And so each router that touches it decrements that field. And here we see that the R1 has decremented the field to 0. And so now sends back a different type of ICMP message. Okay, so there's our type. This happens to be a time exceeded message. and this goes back. Now traceroute actually repeats this action a couple of times. Oh, now what just happened there? Let's grab the one from the host. There we go. We can see here that the time to live is 2. So R1 decrements this by 1. And so the message that goes from R1 to R2 has a time to live of 1. Okay? And then R2 decrements this to 0 and sends the ICMP time exceeded message back. And we can see this comes from 4.2, and it is another time exceeded message. So we'll bat this back and forth a couple of times, and at some point we will increment the time to live to 3. And I think this time will be the one. Okay, so let's see what this one has. Time to live of 3. So that means R1 will decrement it to 2, R2 will decrement it to 1, which means it'll get all the way to the destination at this point. And there we have it. So that is how traceroute works. Now, like the extended ping, we also have extended traceroute, and it's the same thing where you can specify the target address, but the important part is being able to specify the source address, and that would give you an opportunity to test different pathways, or at least test the response to different source IP addresses. Now, ping and traceroute are both terrific tools. I would absolutely encourage you to come to know and love them as I do, but they have limited visibility and they can't show you how something is configured. They can show you where problems are, and then you can sort of make some suppositions about what you think is wrong, but what we really need sometimes is access to the device. So, Telnet and SSH. And so today we're going to remind ourselves how to SSH to a device. Now, the really cool thing is that routers and switches also have SSH clients. So that becomes really, really helpful if we can't get to a device from another device, but we can SSH to a device that's closer. And I'll show you exactly what I mean here. It also allows us to hop around a little bit between devices if we believe that something like a routing protocol is misconfigured or we have some other connectivity problem. Now I'm going to do some review with you. So I'm going to recall you to chapters 4 and 6 for some of the configuration that we're going to do. Now, just as a reminder, we can have passwords of all kinds. So we can have login passwords, we can have enable passwords. You can have different passwords for different lines. You can have local names and passwords. You can specify the transport type on a line. And then, of course, when you decide to do SSH, it has its own configuration, right? The host name, the domain name. You got to generate the keys and have a user account to do that. Well, let's take a look at what I did for that. Now, first up, I'm going to point out that I've got this node here. This is a console connection. And so we'll start there. So I'm going to use the terminal. And we're going to configure. Now, I'm going to go all the way out, right? And I just want to connect via the terminal. This is not an enable password. This is as soon as I go to connect. And so I've got to log in right here. That gets me to the user prompt. Now I have an enable password. So that was a different level entirely. So let's take a look at the running config and see what I did. So I have this first enable password. Remember our host name command that helps me keep things straight, mostly because the prompt is there. I've got this username that I created for myself. We'll use that here in a second. Oh, I just realized SSH version 1, very, very bad. Now this is, I forgot to do this. We'll do this right now too. So this is the IP host command that allows me to ping by name on a router when I don't have DNS active. let's see what else we did. Let's go down to my line commands. Now this is the login requirement for my console. And here is the login requirements for my VTYs. So what I'm specifying here is that we're going to require logins on all of these things, and that in this particular case we're going to do some SSH, but we can also specify that I'm going to be using some local accounts to do this. So these are why we have all of these different layers of passwords and logins and everything else. Now before I leave here, I said that we could do a ping. Now if I just ping R2, okay, we get this success rate, and what it's actually doing is pinging r2.example.com, which is this definition that I made up here. Okay? All right. Well, that is our sort of reminder about all of the logins. So now let's go ahead and remind ourselves about the SSH connectivity. So here is, we're going to do, let's do this one first. Well, first we'll try to ping 172.16.4.2. That's this side. Why is that working? All right, so I just realized that some of my wonky behavior here has been because I forgot to change the mask back, but here we go. Let me, let's take an example here. If I try to ping 172.16.4.2, right, it doesn't work. I can't get out here, which also means that I couldn't SSH to that particular device. But if we remember that I created a username and that my router has an SSH client, then here's a way that I might get away with this. Okay, so what I'm going to do is we're going to close this, and I'm going to use the SSH client. So I'm going to SSH to 172.16.1.254, and I'm going to use the username Bruce, which is the one you saw that I had set up. And this will be the password that I have for that account. Okay, now I have the enable password, which was hi there, I think. Okay, so now I'm SSH over to R1, but we know that 172.16 can't SSH to 172.16.4.2 because I forgot to do the default gateway. I can use the SSH client on my router. Let's do this right. SSH. So I can use the SSH client to log into a neighbor from the router that I just SSH'd into. So I'm going to use the same account. Oops. And now I'm going to go, all right, what IP address am I going to? Well, now let's see if I can get to 4.2. And the answer is I can, because router number 1 has the ability to get to router number 2. So take a look at how the prompt changed. So now I'll do enable here. And now I have the configuration of router number 2. If I exit out of this, notice that the prompt now is back on R1. So there we see that I can not only SSH from a host to a router after configuring the host for SSH, right? We got to do the username, the domain name, the host name, the crypto key generate, and then set up our transport in with SSH if we want to specify SSH only. But then, of course, we're going to do not only this connection, but we saw that the router itself can be used as an SSH client. Now, the really nice thing is that from here, I can hop all over the network. In fact, I could SSH to a router 2, and then from there, SSH to someplace else. But there we go, SSH and the SSH client on the router. Well, the reason we wanted to make sure we had a handle on this chapter, and we wanted some troubleshooting tools, that we really wanted to understand our static routing and really be able to troubleshoot it. Why? Because we're about to do OSPF. So the Chapter 21 look ahead is routing measures. We're going to talk about metric and admin distance and even prefix length. Understanding OSPF concepts. We're going to do a single area OSPF build. We're going to talk about adjacency, point-to-point areas, broadcast areas, and the router ID. Going to be very exciting, our first routing protocol. All right, this has been Chapter 20, IPv4 route troubleshooting, or static route troubleshooting especially. We went over ping and trace route. We saw that there are both standard and advanced or extended versions of that. We reviewed logins, right? We can we can have a password on the device, an enable password. We can do SSH passwords with user accounts. And hey, we figured out that routers and switches have built-in SSH clients themselves, so we can hop all over the place. Whew, good stuff, good stuff. Hey, like and subscribe if you are ready to troubleshoot, and may those packets always reach their destinations, no matter what kind of transport you're using. And remember, this is CCNA. We're heading for OSPF. You can do this. All right, so this has been the Do I Know This Already questions for Volume 1, Chapters 11 through 20. Don't forget all of the materials that are out there. Lots of YouTube channels, not just this one, but also the practice exams. If you bought the book, you get all of this practice material through Prentice Hall and everything else. So take advantage of those. Well, like and subscribe if you'll dig this idea. May those packets always reach their destinations, no matter how you did on these practice exams. Remember, they're just practice. And hey, this is CCNA. We're doing this together, and you can do this too.